Hi guys, it's Jaden
Gracie,
And Jason,
doing fluid electrolyte
acid base.
balance.
Alright, so in fluid and electrolyte, there's two main compartments and they're occupied by one. There's the intracellular compartment, which is intracellular fluid, which is almost 2/3 by volume, is in the ICF, which consists of trillions of tiny individuals compartments, and accounts for 25 of the 40 liters of the body. Then there's also the extracellular fluid, which is the ECF, which is remaining 1/3 of the body water in outside cells and constitute the body's internal environment. There's two subcompartments, which is the plasma and interstitial fluid. And there's electrolytes, which are chemical compounds that dissociate into ions in water, and due to the ions being charged particles, they can conduct electrical current. This includes inorganic salts, both inorganic and organic acids and bases, and some proteins. Then we got left the non-electrolyte, which have bonds that are usually covalent, and this prevents them from dissociating in solutions, and this includes glucose, lipids, creatine, and urine. Alright, so we've got the chemical equations now. Sodium chloride dissociates into sodium and chloride, and it's an electrolyte that has two particles. And then we got magnesium chloride, which dissociates into magnesium and two chloride, which that is an electrolyte with three particles. And then we've got glucose, which goes just to glucose in dissociation, which is a non-electrolyte, so it does not dissociate. And then it is one particle. Then we've got milliequivalents per liter, which the equation is m, big E, little q, per liter. And then it is the measure of electrical charges in 1 liter of solution, which in order to compute it, so the computation of the electrical charges contributed by any ion using the equation is the milliequivalents per liter, which is the ion, which is milliequivalents per liter equals ion concentration, which is mg divided by the liters, so magnesium divided by liters, over the atomic weight of an ion, so mg divided by mmol. And it's all times the number of electrical charges in one ion. And then we got fluid exchange, which exchanges between plasma and an interstitial fluid across capillary walls, and then the exchanges between the interstitial fluid and fluid in the ICF occur across the plasma membranes.
Metabolic water. Most water enters the body through ingested liquids and solid foods, typically about 2,500 milliliters a day in adults. Body water produced by cellular metabolism is metabolic water or water of oxidation. Water output. It occurs through several routes. Insensible water loss is when water is vaporized out of the lungs or diffuses directly through the skin. Sensible water loss is any water that can be measured after it is lost through urine, sweat, and feces. ADH. The amount of water reabsorbed in the renal collecting ducts is proportional to ADH release. The thirst mechanism is the driving force for water intake and is governed by the hypothalamic thirst centers. Osmoreceptors detect ECF osmolarity through changes in plasma membranes like stretch that can result from gaining or losing water. Dry mouth happens when the blood's osmotic pressure increases. The salivary glands produce less saliva because the osmotic gradient is drawing water from the blood into the salivary ducts decreases. Dehydration is defined as fluid loss, either through the loss of water by itself or the loss of water and solutes together. It is a common sequel to hemorrhage, severe burns, prolonged vomiting, diarrhea, profuse sweating, water deprivation, and diuretic abuse. It may also be caused by endocrine disturbances such as diabetes mellitus. Another serious consequence of water dehydration from plasma is inadequate blood volume to maintain normal circulation and ensuing hypervolemic shock.
Hypotonic hydration, it's a type of cellular overhydration. The ECF is diluted, sodium content is normal, but excess water is present, and sodium concentration is low. Hyponatremia promotes net osmosis into tissue cells, which causes them to swell as they become abnormally hydrated. Then we got edema, which is swelling, and it's atypical accumulation of fluid in the interstitial space, leading to the tissue swelling. Then we got the electrolyte balance, which refers to the salt balance in the body, and it is important in controlling fluid movements and providing minerals essential for excitability, secretory activity, and membrane permeability.
Aldosterone. ACTH targets adrenal cortex, which causes aldosterone release, which then targets the kidney and causes sodium reuptake. ANP, natriuretic peptide, reduces blood pressure and blood volume by inhibiting nearly all events that promote vasoconstriction and sodium and water retention. Estrogen. It is chemically similar to aldosterone, and it enhances sodium chloride reabsorption by the renal tubules. Most women retain fluid as their estrogen levels rise during the menstrual cycle. Progesterone has a mild diuretic effect, which is thought to be due to its blocking aldosterone receptors. Glucocorticoids. Cortisol and hydrocortisol enhance tubular reabsorption of sodium, but also promote an increase in glomerular filtration rate that may mask their effects on the tubules.
So a couple important points with the chemical buffer system before we go into depth. Anything that causes a shift in H+ concentration in one fluid compartment simultaneously causes a change in the others. The buffer system buffers one another, so the entire buffer system resists any drifts in pH. Now we have acids. Acids are proton donors. Strong acids dissociate completely. They can dramatically change a solution's pH. Weak acids dissociate only partially. They have much smaller effect on pH. With weak acids, they're efficient at preventing pH changes, and this feature allows them to play an important role in chemical buffer system. Bases. Bases are proton acceptors. Strong bases are those that dissociate easily in water and quickly tie up hydrogen ions. Weak bases are less likely to accept protons. Chemical buffers. A system of one or more compounds that resist change in pH when a strong acid or base is added. They do this by binding hydrogen ions whenever the pH drops and releasing them when pH rises. There are three major chemical buffer systems. There's the bicarbonate, phosphate, and protein buffer. Over here, we have the bicarbonate buffer system, which is a mixture of carbonic acid, which is H2CO3, and its salt, sodium bicarbonate, NaHCO3, a weak base. Although it buffers the ICF, it is the only ECF buffer. Carbonic acid, a weak acid, does not dissociate to any great extent in neutral or acidic solutions. When strong acids like HCl is added to this system, existing carbonic acid remains intact. However, the bicarbonate ions, or the salt, act as a weak base to tie up the hydrogen ions released by the stronger acid, hydrochloric acid, forming more carbonic acid. And then here we have the chemical equation for the bicarbonate buffer system. So here we have the chemical equation for the bicarbonate buffer system, which consists of hydrochloric acid, sodium bicarbonate, carbonic acid, and salt. It converts the weak acid, carbonic acid, and HCl, which lowers pH slightly. A weak base, such as sodium bicarbonate, does not dissociate further under alkaline conditions or basic conditions. The added base forces the carbonic acid to dissociate further, donating more hydrogen ions to tie up the hydroxide ion released by the strong base. In this equation, we have sodium hydroxide, carbonic acid, sodium bicarbonate, and water. The net result is that a weak base, sodium bicarbonate, replaces a strong base, sodium hydroxide, so the pH of the solution rises very little.
Alright, so the phosphate buffer system. The operation of the phosphate buffer system is nearly identical to the bicarbonate buffer system. The components are sodium salts of dihydrogen phosphate and monohydrogen phosphate. NaH2PO4 acts as a weak acid. Na2HPO4 with one less hydrogen atom acts as a weak base. Strong bases are converted to weak bases, and hydrogen ions are released by strong acids and are tied up in weak acids. Then we got the chemical equations, which HCl plus NaHPO4, and that makes NaH2PO4 plus salt, or NaCl. And then we've got NaOH plus NaH2PO4, which creates Na2HPO4 and water, or H2O.
All right, next we have the protein buffer system. Protein in plasma and in cells are the body's protein buffer system. Proteins are polymers of amino acids. Some amino acids have exposed groups of atoms called carboxyl groups, which is negative COOH, which are organic acid groups that release hydrogen ions when pH rises. Other amino acids have exposed groups that can act as bases and accept hydrogen ions. An example of this is an exposed negative NH2 group can bind with a hydrogen ion, becoming NH3+. And this is an example of that here. You see the equation down here, the R with the negative NH2, and then you have the hydrogen plus ion. That hydrogen plus gets sucked up into the equation, becomes NH3. A single protein molecule can function reversibly as either an acid or a base, depending on the pH of its environment. Molecules with this ability are called amphoteric molecules. Respiratory regulation of hydrogen. The respiratory and renal systems work together to form the physiological buffering system that controls pH by regulating the amount of acid or base in the body. The respiratory system eliminates CO2 and acid from the blood while replenishing its supply of O2. Carbon dioxide generated by cellular respiration enters red blood cells in the circulation and is converted to bicarbonate ions for transport in the plasma. As you can see here, the chemical equation, CO2 plus H2O can form either way to H2CO3, and then it's double again to hydrogen plus HCO3 negative.
The first set of double arrows indicates a reversible equilibrium between the dissolved CO2 and water on the left and carbonic acid on the right. The second set indicates a reversible equilibrium between carbonic acid on the left and H plus, or hydrogen ions, and bicarbonate ions on the right. Then we've got renal regulation, a long-term mechanism for controlling acid-base balance, and the kidneys are the ultimate acid-base regulatory organs. Chemical buffers tie up excess acids and bases, and are temporarily but cannot eliminate them from the body. Alright, so lungs dispose of volatile carbonic acid by eliminating CO2. Only the kidneys rid non-volatile acid, for example, phosphoric, uric, and lactic acid. Losing an HCO3 negative from the body produces the same net effect as gaining a hydrogen ion. To reabsorb bicarbonate, the kidney has to secrete hydrogen, and when it excretes excess HCO3 minus, hydrogen is retained, not secreted. Then we got the bicarbonate reabsorption, which the kidneys can't reabsorb HCO3 minus from filtrate, but generates it from within the tubular cells to then secrete it into the peritubular cavity. The number of HCO3 minus generated within the tubule cell is the same as the number of hydrogen pumped out of the tubular cells into filtrate. Even though no HCO3 minus molecules ever pass from filtrate into tubular cells, the net result is removal or elimination of HCO3 minus from filtrate. Generating new bicarbonate ions is done via excretion of buffered hydrogen and uses the phosphate buffer system in filtrate. The result is an increase in blood pH, adding bicarbonate ions, while urine pH is decreasing, adding hydrogen ions. It is also done via ammonium excretion, which involves formation of ammonia, NH3, which is from amino acid glutamine within tubular cells. And then filtrate, Na4 plus, or ammonium plus chloride, it becomes ammonium chloride and is excreted in urine. Bicarbonate ion secretion. When the body is in alkalosis, intercalated cells, or type B cells, in the collecting ducts exhibit net bicarbonate secretion while reclaiming hydrogen to acidity in the blood. In respiratory acidosis and alkalosis, respiratory acidosis, a common cause of acid-base imbalance, most often occurs when a person breathes shallowly or when gas exchange is hampered by disease such as pneumonia, cystic fibrosis, or emphysema. The normal partial carbon dioxide levels are about 35 to 45 millimeters of mercury. And in acidosis, partial CO2 levels are greater than 45 millimeters of mercury, and pH is less than 7.35. Respiratory alkalosis. When carbon dioxide is eliminated from the body faster than it is produced, an example would be hyperventilation. Partial CO2 levels are less than 35 millimeters of mercury, and pH is greater than 7.45. Metabolic acidosis and alkalosis. Metabolic pH imbalances include all abnormalities or acid-base imbalances, except those caused by too much CO2 or too little CO2 in the blood. Metabolic acidosis. It is recognized by low blood pH and bicarbonate levels. The causes of it is too much alcohol accumulation or lactic acid during exercise or shock. Normal bicarbonate levels are 22 to 26 milliequivalents per liter, and in acidosis, bicarbonate levels are less than 22 milliequivalents per liter, and the pH is less than 7.35. Metabolic alkalosis, indicated by rising blood pH and bicarbonate levels, much less common, and in alkalosis, bicarbonate levels are greater than 26 milliequivalents per liter, and pH is greater than 7.45. And causes of it are vomiting, the acidic contents of the stomach, or too much antacid.